What's up, guys? Today we're going to be talking about linear transformations for probability distributions. So we're going to start off with a brief review. When I was talking about discrete random variables and discrete probability distributions, I said that the sum of all the corresponding probabilities for all the possible values that x could take on has to equal 1. Another thing is that since this equals 1, if I multiply that by some value like r, then that has to equal 1 because 1 times r is just r. In other words, r times the sum over all the ith indices of p of x sub I is equal to r. Another thing that we said is that the average of any function of x, our discrete random variable, is equal to the sum over all the ith indices of f of x sub I multiplied by p of x sub I, which is equal to f of x sub 1 times p of x sub 1 plus f of x sub 2 times p of x sub 2 all the way up to f of x sub n multiplied by p of x sub n. Whew. And for a continuous random variable, it's different though. Instead of having a summation over all the ith indices, we replace that with an integral. And instead of x being allowed to take on certain values, it's allowed to take on the entire continuous spectrum. So in this case, the probability of x equaling exact value is 0, as mentioned in my other video. If you haven't watched that, please do. And another thing that's true is that if we integrate over the entire range in which the probability distribution function is defined, then we should get 1. And since this equals 1, if we multiply that by any number, we're just going to get that number back. In other words, r times the integral of p of x dx is equal to just r. With that being said, the average is very similar. The average of f of x, which in this case is our continuous random variable, is just equal to the integral over the entire range in which the probability distribution function is defined of f of x times p of x dx. So why am I rehashing all of this, first of all? The reason why is because we're going to use these to derive things called linear transformations. So you remember how I was saying that the average of a function of a discrete random variable is equal to the sum over all the ith indices of f of x sub I times p of x sub I. So what if f of x is actually a linear function? So that's what's presented here. So in this case, y is our linear function, which is equal to mx plus b. And m and b are both constants, where x is our other discrete random variable. So in this case, we want to find the average of y, but we're going to do it different than the ways that I showed you guys in the videos presented before. Here, I'm going to show you what happens if we actually just work out the math. So here I'm finding the average value of y, and that's going to be equal to, as we defined before, the summation over all the ith indices of y of x sub I times p of x sub I, where y in this case was our f of x. And since we know what y is, we can plug that in and we're left with the summation over all the ith indices of m of x sub I plus b, all of that being multiplied by p of x sub I. And since that's all being multiplied by p of x sub I, we just distribute that term to each one of the other terms in the linear equation. So we're just left with m x sub I times p of x sub I plus b times p of x sub I. But since this is all being summed over, we can actually distribute the summation over each term as well. So we're left with this equaling the summation over all the ith indices of m times x sub I times p of x sub I plus the summation over all the ith indices of b times p of x sub I. Notice here that we actually have another rule that we can apply. Because m and b are both constants and they're multiplying each term that we're summing over, we can just factor it out. In other words, we can just pull it right out of the summation. So then this equals m times the summation over all the ith indices of x sub I times p of x sub I plus b times the summation over all the ith indices of p of x sub I. Notice in these two terms now that x sub I times p of x sub I is actually the very definition of what we said the mean was. And the summation over all the ith indices of p of x sub I is equal to 1, as we said in the previous slide. So this entire thing can actually be summarized to say that the average of y is just equal to m times the average of x plus b. So if y is related to x as a linear equation, and we know what the mean is for x, then we just evaluate y where x is equal to that mean in order to find the average value of y. So for a continuous random variable, it actually is very, very similar. And the reason why is because a summation and an integral are both linear operators, so they both obey the same principles. So if we're trying to find the average value of y, that's equal to y of x times p of x dx, and we integrate that over the entire region in which p of x is defined. And so using those same principles, we're left with m times the integral of x p of x dx. And the integral of x p of x dx is actually what we define the mean for a continuous random variable. And next we're left with plus b with the integral over p of x dx, which is just equal to 1. So we're left with b. So we're just wrap this up and say that it's equal to m times the average of x plus b. And so if we know that y is related to x as a linear equation, then we just plug in the average value of x in order to find the average value of y.